polar coordinates. So, polar coordinates, another way of describing a point in the two-dimensional plane. So one way to describe a point, x comma y, is just to go, like over x and up y. Over x and up y. But another way to think about this is instead of going over and up or horizontally and vertically, we can measure an angle and then talk about how far from the origin we have to go. So we can measure the angle from the positive x-axis and say that angle is theta, and that distance we're going to go from the origin to the point is some r. And the way we relate these is that, well, I think you can see the Pythagorean theorem relation, or the Pythagorean relations here. We have that x squared plus y squared equals r squared. Some people solve for r, usually not. We can say that cosine of theta equals x divided by r, or more normally written as x equals r cosine of theta. Similarly, sine of theta equal to y over r gives us that y is equal to r sine of theta. And lastly, which doesn't come up as much, but sometimes does, tangent of theta is equal to y over x. And occasionally we solve for theta and say that theta is equal to the inverse tangent of y over x. Although you have to be a little bit careful about that because inverse tangent has a limited range. So these are the equations that you need to remember to help you get back and forth between polar and rectangular coordinates. Okay. Really want to get to the graphing stuff, but we feel like we have to talk about a few things before we get there. So typically with polar coordinates, we usually like to think of r being a positive number. So you measure some angle and then you go some distance. But technically r can be negative as well, which means you turn around and go the opposite way. So for example, sure. The point 2, 2. If I want to describe this using polar coordinates, one most obvious way of doing it would be to say, okay, well, my angle is, if I've gone over and up the same amount, what is my angle? 45 degrees. Or in radians?
Power 4?
Right. Which we also could have found by doing the inverse tangent of 2 over 2. Which is the arctangent of 1, which is pi over 4. And then the radius we could find, well, we know that the x value is 2, we know that the y value is 2. So r squared is x squared plus y squared, which is going to be 4 plus 4, which is 8. So r is going to be the square root of 8. Or if you prefer to simplify that, 2 times the square root of 2. So in polar coordinates, we do write the r first and the theta second typically. We could describe this as 2 root 2 comma pi over 4. But you could also describe it as negative 2 root 2 comma 5 pi over 4. I could go all the way around to an angle of 5 pi over 4. And then instead of going in the positive direction for that angle, turn around and go in the negative direction for that angle. So a negative r value just means you flip the direction you're going. Instead of going in the direction of the angle, you go in the opposite direction of the angle, or you go 180 degrees different, or add pi or subtract pi, whatever you want to say. Yeah.
Wouldn't that make that point in the third quadrant?
No, it wouldn't. It looks like it would, but the thing is, right, so I'm going around to this angle here, right? But then from the origin, I'm going to go negative in the opposite direction I started. I was pointing in. So the angle is pointing me in the 5 pi over 4 direction, but then the negative radius means I turn around and go the opposite way.
Okay.
So just a couple more examples. If I was going to describe the point r theta, let's pick some other angles. Let's say my radius was 4 and my angle was pi over 2. That would describe to me the point that was going straight up. So it'd be up 1, 2, 3, 4. That point there in polar coordinates is 4 comma pi over 2. In rectangular coordinates is 0 comma 4.
So is the top of the line to the x-axis in between there's that pi over 4?
Say that one more time.
Like the top of the orange line to the x-axis, like the distance in between.
Right, like that there.
Yeah, is that pi over 4?
That angle is pi over 4.
Oh, okay.
And then this angle here is 5 pi over 4.
Oh, okay. Okay, starting at the x-axis.
We're always starting at the x-axis. Yeah, well, I should say, we're always starting at the positive x-axis. So the right side.
So is the only way to get, like in the first example, the theta percent, like say it was more complicated and it wasn't just a 45
Sure.
over one slope, you would have to use arctangent.
Right, exactly. So
You have
here,
to know arctangent.
right, so or just be stuck with it. So for example, let's say I want to describe the point in space. I'm just gonna make up something terrible. Let's say we have the rectangular coordinates, -2 comma +3. Come over here. Like that. I know my angle should be between 90 degrees and 180 degrees, or between pi over 2 and pi. So I can find r pretty easily. I know that r squared equals x squared plus y squared. So that means r squared is equal to 13. So r is equal to the square root of 13. And then this angle, so here's why we have to be a little bit careful. So certainly, I could say the tangent of my angle is equal to opposite, so y over x, 3 over -2. Or if you prefer, -1.5 or -3/2. So here's the problem. If you are not careful, you're going to actually describe the wrong point. If you say that theta is the arctangent of -3 over 2, it's not the right angle. Because the arctangent function spits out angles between -pi over 2 and +pi over 2. And this angle is bigger than +pi over 2. So this angle here, that's the arctangent of -3/2, is actually that angle right there.
It went the other direction.
Right, because the arctangent function only gives you angles that are negative in quadrant 4 or positive in quadrant 1. So one sec. So if you wanted this angle here, what you would have to do is you have to take the arctangent of that number, which I don't know what that is. Right? I'd actually have to plug it into a calculator and get something terrible, and then add pi to it. So our actual answer here is that theta is the arctangent of -3/2 plus pi.
So if you were to put in a positive theta and have r be positive as well, would they mark you wrong?
It would be wrong. Yeah. So another way to get around this, if you wanted to, so one way to describe this point, our r comma theta could be the square root of 13 comma the arctangent of -3 over 2 plus pi. An alternative answer, which would also be correct, would be to say that r comma theta is -√13 comma arctangent of -3/2. Because that gives you the right direction, and then we flip it around to go the opposite way. What I would say is you probably don't have to worry about this too much. Like you shouldn't be super stressed about this. This is not going to come up really probably ever. But
Really?
yeah, I mean, nobody's usually when you're taking an exam on this kind of stuff, people really aren't asking you to describe other points in different ways. They're usually talking more about like graphing some sort of.
Like you were given an equation.
Right.
And yeah.
Let me give you one more example and then we'll move on. So let's say I want to describe the point x comma y equal to, I have to be a little bit careful here. Sure. Let's say I want to describe the point -2 comma -2 √3. which I picked for what will soon become obvious reasons. So let's see, going 2 to the left and I'm going more than 2 down. Root 3 is about 1.7, so it's about 3.4. So we're over there. And I'm trying to both describe this angle theta, which is certainly not in the range of the arctangent function, and the radius. And the radius is always going to be easy, right? The radius, we're just going to do r squared is -2 squared plus -2 root 3 squared, which ends up being 4 plus 4 times 3, which is 16. So we're going to get that r is equal to 4.
It always is positive, because could it be negative?
Technically, it could be positive or negative, but I'm going to try and do. We default to r being positive. We don't make it negative unless we really, really, really have a good reason to, or the function we're dealing with is giving us negative r values. So now, if I want to find the angle here, well, if I find the arc tangent of -2 root 3 over -2, that's the arc tangent of root 3. Let me ask you all, can you tell me the angle whose tangent is equal to positive root 3?
Either 3 or 6.
It's either 3 or 6. It's 3.
That's my problem.
Bigger value, bigger for tangent, the bigger angle means the bigger value, the smaller angle means the smaller value. So if it was root 3 over 3, which is the other value we look for, the angle is smaller because it's a smaller value. Question?
How do you know, like, for both of these problems, when to use tangent, when to use arctangent?
Well, so the thing is, if I'm going from rectangular coordinates, x and y, to polar coordinates, r and theta, the way I find r, and the way I find theta is by doing the inverse tangent, right? I could have started by writing just tangent of theta equals -2 root 3 over -2. And actually, I probably could have just found it that way. I could have said, oh, yeah, tangent of theta is equal to root 3, which means theta is equal to pi over 3. But I think you all can see from my picture, pi over 3 is not the right angle. What do I actually need for my correct angle?
Over 3 plus pi.
Right, I need pi over 3 plus pi, because pi over 3 is this angle here, and I need to be pi more radians than that.
So is it pretty general that it's in the left side? What is that point?
If it's in quadrant 2 or 3, arctan is not going to give it to you right off the bat. Typically, yeah.
Okay.
Now I will say we could totally describe this point in polar coordinates as r comma theta equal to 4 comma 5 pi over 3, or if you wanted, we could also equivalently describe it as r comma theta equal to -4 comma pi over 3. Both of those would give you the same point in space. So what's kind of interesting about polar coordinates is they're not unique, whereas rectangular coordinates are. There's only one way of describing this point in space using rectangular coordinates. You go left so much and down so much. It's kind of interesting. Okay. Let's talk about converting equations from rectangular to polar or vice versa.
So what's in red ink, that's the wrong way to.
So in red ink, what we're doing is we're saying the angle is pi over 3. So we're going in that direction. That's the positive direction to go, but then we're going -4. So we go that way.
They're both okay.
They're both okay. So basically, if you change the sign of your r value, you have to change your angle by 180 degrees or pi radians. Technically, I could have done something extra stupid and said it was -4 comma -2 pi, or sorry, pi over 3. I could have said it was negative, I don't know, 7 pi over 3. There's lots of other dumb angles I could use. Usually we try to keep our angles between 0 and 2 pi, or maybe it's slightly negative. Let's look at some other things. So when you're converting between Cartesian and polar, or polar and Cartesian, usually you're trying to make an r cosine theta or an r sine theta show up. Here's what I mean. So I want to convert to polar. So I'm going to start with the straight line x equal to 3. Not very exciting. So when I'm converting from Cartesian to polar, it's pretty easy. We know that x equals r cosine theta, y equals r sine theta. So all I'm going to do is replace every x with r cosine theta and every y with r sine theta. And also, if I happen to see an x squared plus y squared, instead of making more work for myself and saying it's r squared cosine squared theta plus r squared sine squared theta, I'm just going to say, oh, I know it's r squared times 1. So here, I'm just going to get r cosine theta equal to 3. Usually, we write r as a function of theta, if possible. So we often think of r as the output and theta as the input. Because if you're graphing this stuff, you're gonna be like, okay, well, I'm gonna go this much angle and then find out how far I go. It's weird to say, how far out do I go, and then determine what angle you're living at. So it makes sense to think of theta as the independent input and r as the dependent output. So here I'm going to write r equals 3 divided by cosine theta, or preferably r equal to 3 secant theta. So graphically, here's what this looks like. There's my xy coordinate system. Here's my line. X equal to 3, or r equal to 3 secant theta. Which, if you think about it, does make sense. If you let your angle be some theta, well, here's the r value, and this value here is 3, and certainly secant of theta is r over 3. So r is equal to 3 secant theta. And you can see that as your angle gets closer and closer to pi over 2, where secant of pi over 2 is undefined, because it's 1 over cosine of pi over 2, which is 1 over 0. But as that angle gets bigger, you're going to get larger and larger r values. So you're just going to get the higher and higher points of, like, as that line goes up and up and up. Kind of weird. Kind of neat, though.
What's the 3 on the graph mean?
That's how, so this line is x equal to 3.
Right.
So this distance literally is 3.
Yeah.
Or you can do something fun like y equal to x, which we already know what this is. If you graph the line y equals x, what's always true about this line? Well, the angle never changes. So I think we could just say, well, this line, the polar coordinate is, or the polar equation is theta equals pi over 4. And there is no r, because r can be anything. Right? I want this point and 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 this point, right? I want all those ones. Now, if you were actually doing the work, how would you do this? Good question. You might just replace x and y with the respective equations. So you might go, okay, well, I'm going to have r sine theta equal to r cosine theta. Divide both sides by r. Divide both sides by cosine. Sine over cosine is tangent theta equal to 1. Oh, theta equals pi over 4. So that's another way you could get there. It's kind of like how when you have like the line x equals 3, y can be anything. Here in the equation, theta equals pi over 4, r can be anything. And then things just start to get weird. So for example, if I have the line y equals 2x plus 1, I know what that looks like, has a pretty regular Cartesian equation, right? That's a pretty straightforward line. But if you write it in polar, so what I want to point out here is like some equations just make more sense in one system versus another. Later on, when some of you take 21D, you'll talk about spherical and cylindrical coordinates. And the reason they're called those things is because it makes it's really, really easy to describe a cylinder using cylindrical coordinates. It's really easy to describe a sphere using spherical coordinates. It's really easy to describe a rectangle using rectangular coordinates. it's really weird to describe a straight line using polar coordinates, right? It's just not something that's typical, but we can still do it. I'm gonna say r sine theta equals 2r cosine theta plus 1. And then without any sort of other intuition, my thought is always going to be to solve for r. So I'm going to have r sine theta minus 2r cosine theta equal to 1. Factor out the r. So r times sine theta minus 2 cosine theta equals 1. And then r is equal to 1 divided by sine theta minus 2 cosine theta. It's kind of funky. I feel like I saw an interesting problem on one of the homework assignments the other day. Let's see. No, that's parametric. Not in there. Oh, it's not. Let's do that. Oh, that's not a really neat one. Thought I saw one that was really cool, but it's not. Oh well. So, yeah. Couple other not too terrible ones. If we had like x squared plus y squared equal to 25. Now, we're going to do the work, but I know you all know this is what kind of shape. It's a circle with what radius? Great. Here's my polar equation. R equals 5. Which really we could get by just replacing x squared plus y squared with r squared. R squared equals 25, so r equals 5. Okay, let's look at a little bit more interesting of a question. What if we had another circle, but instead it was, what circle do I want here? Sure, let's do x plus 4 squared plus y squared equal to, I have to be careful here. Centers that, I want the radius to be that, right? Sorry, 4, yeah, 4. Here's another circle, but it's not centered at the origin. So I can't say the radius is 5 or 4. So here I'm actually going to do the thing. I'm going to, and do I want to multiply this out first? No, I don't think I want to. So I'm just going to replace. I'm going to rewrite. Oh,
If you multiply it.
Yeah. So in the notes here that I have, the person who's doing it just replaces right away. But I think it's worth multiplying out because I know what's going to happen. So if you multiply this out, here's what happens. You get x squared plus 8x plus 16 plus y squared equal to 16. 16's cancel. What's x squared plus y squared?
R squared.
Right. And 8x is going to be 8 times r cosine theta. And then we can solve for r. So I'm going to factor out an r. R times r plus 8 cosine theta equals 0. So either I get r equal to 0, which doesn't really make sense if I have the graph of a circle. Right? It doesn't make sense to say that the radius is just 0. Right? Because this circle here is the circle centered at -4 with a radius of 4. Sorry, at x equal to -4. Or I get r equal to -8 cosine theta. And that is actually the graph of the circle. In polar, or I say the way to describe the circle using polar coordinates.
So that's your final answer.
Yeah. What's super cool is that this is kind of generally true, meaning if you're ever graphing r equal to some multiple of cosine theta or r equal to some multiple of sine theta, you're going to get the circle centered on the x-axis with a radius of the absolute value of a over 2 and centered at a over 2 comma 0. Now, I would never actually do that if I was writing it out. If I was actually graphing this, if someone said, James, what's the graph of, r equal to 10 cosine theta? Here's what I would actually do. I know I've merged into the graphing polar coordinate stuff. So I would say, I know it's a circle. I know I really have to go to the bathroom. I was trying to make it, I'm not going to make it. What's the center of the circle?
I don't know.
Okay, so here's how I would graph it. So here's the thing, graphing this actually is a pain in the ass, right? Like if I was actually going to plot points, the way I would do this is kind of annoyingly. I would start with my angle and say, okay, I'm going to pick like 0. Let's be complete about it. Pi over 6, pi over 4, pi over 3. Hi, you here for 21B? Okay. Pi over 2, etc. So cosine of 0 is 1. 10 times 1 is 10. Cosine of pi over 6 is root 3 over 2. 10 times that is going to be 5 root 3, which is about 8.5. Pi over 4, cosine of pi over 4 is root 2 over 2. So you're going to get 10 times root 2 over 2, which is 5 root 2, which is about 7. Pi over 3, cosine of pi over 3 is 1/2. 10 times 1/2 is 5. Pi over 2, cosine of pi over 2 is 0. So here's what this looks like. So when the angle is, let's try it. So this is where, like, this is way too much work for this problem. Here's my angle pi over 4. Here's my angle pi over 6. Here's my angle pi over 3. So when theta is 0, my value is 10. Theta is pi over 6, my value is 8.5, which is maybe about right there. Right, I kind of think about that being like that. Right, it's not straight down, it's arcing down along like the circle. When theta is pi over 4, my value is 7. So maybe 7 go like right there. And then when theta is pi over 3, my value is 5. And now this hasn't come out perfectly because my drawing skills are not great. What this should actually look like is we should basically be getting something that does this and is the top half of the circle, which I know doesn't look excellent, but it actually is. Like I know again, right? My value is not maybe perfectly placed. So this is a circle of radius 5 centered at 5. And if you do the rest of the angles from pi over 2 to pi, you're going to get back to this other half over here. It's kind of cool. So if I was actually graphing this, though, here's how I would actually graph it. I'd be like, oh, r equals 10 cosine theta. Great, I know that's a circle. I'm going to pick these two values always.
How do you know it's a circle?
Experience. But we know, you also now know that if r equals anything times just cosine of just theta, or any number times just sine of just theta, you get a circle. And I can show you how. Give me 1 second though. So if I was actually graphing this, here's what I would do. Say, great, I'm gonna let theta equal 0. And when theta equals 0, r is going to be 10 times cosine of 0 is 10 times 1. And then when theta equals pi over 2, r is going to be 0. So here are the 2 points I'm going to get. This point over here at 10, and this point over here at the origin. And then I know it's a circle, and those are the end of a diameter. My circle looks like this. Ah, crap. Except you have to be able to draw a circle. Wow, my circle looks better than that, but you get the idea. And the center is halfway between those two endpoints. Now, let me talk about how you could see it's a circle equationally. So what if you actually want to change this back into a circle? Or back into the Cartesian coordinates that were a circle? You're going to multiply both sides by r. So r equals 10 cosine theta, multiply both sides by r, and get r squared equals 10 times r times cosine of theta. And you all can tell me that r cosine theta is what? is x. And r squared is what?
Wait, yeah, that.
X squared plus y squared. So then, if I rewrite this, I've got x squared plus y squared equal to 10x. I bring the 10x over to the left side. I've got x squared minus 10x plus y squared equal to 0. And now I'm going to complete the square. I'm going to add half of 10, negative 10 divided by 2 is -5. And squared that is 25. Add 25 there and there. Then I've got exactly x minus 5 squared plus y squared equals 25. The center of my circle, 5, 0. The radius of my circle, 5.
Are you completing the square?
Yeah.
Okay.
So again, you don't have to do any of this work to know that it's a circle, but we can do this work to see that it's a circle. So in a similar way, if you were asked to graph r equal to -6 sine of theta, I would plot the same two values of theta. So if theta equals 0, what's r going to be? What's sine of 0? Right, 0. And then if theta equals pi over 2, what's r going to be? -6. Ooh, we're getting a negative r value. So here are the points I'm getting when I graph this. So when r is 0, you just get the origin. Doesn't matter what your angle is. If your radius is 0, you haven't gone any distance from the origin. So I'm definitely getting the origin. And then here's where we have to be extra careful. In the direction of pi over 2, which is the up direction, we're going -6. So in the down direction, we are going 6. So here is r theta equal to -6 comma pi over 2. And those are the ends of a diameter of my circle, which can I actually draw a circle this time? Sure. So this circle has a radius of 3 and is centered at 0, -3. And you could totally find that if you wanted to by doing the same thing for this equation that we did for this equation. First, multiplying both sides by r, then replacing r squared with x squared. Well, in fact, right, we have r squared equals -6r sine theta, and then you'd have x squared plus y squared equals to -6y, and then bring the thing over, complete the square, and you'll exactly get x squared plus y plus 3 squared equal to 9, which is the circle centered at 0, -3 with a radius of 3. Kind of cool. Time is it? Okay, sure. We can also go the other direction with converting, meaning I can give you a polar equation and ask you, like in these examples, actually, right? These are both examples of polar equations that we converted to rectangular. And I can give you some other terrible things as well. For example, I could say, I want to convert to Cartesian, rectangular, whatever you want to call it. You know why it's called the Cartesian plane? Because Descartes is the one who, right? Descartes, the mathematician.
Why is it called polar?
I don't know. I don't know that. Right, Descartes, Cartesian. That's where that comes from. So if I wanted to convert, say, r equal to 4 cosecant theta, if I'm trying to convert to x's and y's, I really want r squareds or r sine thetas or r cosine thetas to show up. That's the thing I need. So if I take this and rewrite it as r equal to 4 over sine theta, and then multiply both sides by sine theta, I get r sine theta equals 4 or y equals 4. And sometimes things aren't super duper stupid. Most of the time they are, though. For example, if I gave you something like r squared equal to sine theta times secant cubed theta, that just looks dumb. Again, I know I'm trying to get things like r cosine theta or r sine theta. It would be tempting, but wrong. Well, not wrong, but just it's not going to give me what I want. To replace r squared with x squared plus y squared, because that seems like a normal thing. The problem is then you're left with sine and secant is the problem. So I would probably first rewrite this as sine theta over cosine cubed theta. And then I'd probably bring the cosine cubed up to the other side. Maybe I would just, no, yeah. Part of me wants to bring this cosine squared, but I think I'm going to cosine cubed. You go r squared times cosine cubed theta equal to sine theta. Now, if I had another r over here, that'd be great, because then I'd have r cosine theta times r cosine theta times r cosine theta. And if I had another r over here, that would also be great, because I'd have r sine theta. So it seems like I should multiply both sides by r. Like a r cubed cosine cubed theta equal to r sine theta, or in other words, y equals x cubed. How weird. I'm sure the way we actually did this was someone started with this and worked back until they got to this. There's all sorts of weird things you can get with converting Cartesian to polar or polar to Cartesian. Yeah.
Would it also be okay to just bring up the cosine squared?
Yeah. So then if, I'm curious what would happen. So if we did that, so if you said r squared cosine squared theta equals sine theta over cosine theta, this is looking like x squared. What's sine over cosine? Tangent. The tangent of theta is y over x. Yeah, that works too. I feel like that's a little harder for me to see personally, but just because I don't see it that way doesn't mean you can't see it that way. So yeah, that works. That works great. So then you've got x squared equal y over x, or y equals x cubed. Cool. Nice job. I like that. So then the other, oh yeah, there's two other things to talk about. So we're definitely gonna run out. Yeah. So the two other things to talk about are the graphing in polar coordinates. And then also sometimes people do the thing where you have to like take derivatives using polar coordinates. Like I think some of you have seen this whole thing where you're doing, so I'll just say this because we don't really have enough time to get deep into graphing right now. So we'll do graphing next time, I guess, if you guys want to. And then I'll say, if you want to take the derivatives, if you want to find like dy dx, because you want to find the slope of a tangent line, well, it's going to be just like we did the parametric derivatives, where I'm going to say dy dx is equal to dy d theta instead of dt over dx d theta. Now, here's the backstory. We know, because of how the polar and rectangular coordinates are related to each other, that y is equal to r sine theta and x is equal to r cosine theta. The idea here is that we are typically, and this is why I said this before, we are usually thinking of r as a function of theta. Right? Most of the time, if we can, we like to solve for r in terms of the variable theta. So really what we're doing is we're imagining this is really, some people like to write f of theta. I prefer to write r of theta. But you can think of it as either r of theta times sine of theta, or if you prefer, f of theta times sine of theta. Similarly, x in terms of theta, or parameterized on theta, is some function of theta times cosine of theta, or if you prefer, f of theta times cosine of theta. So then if you want to take these derivatives, you have to use the product rule. So dy d theta is going to be, well, product rule, the derivative of r, so r prime of theta times sine of theta plus r of theta times the derivative of sine is cosine, over, same deal for the derivative of x. Product rule, the derivative of r of theta is r prime of theta times cosine of theta plus r of theta times the derivative of cosine of theta, which is negative sine of theta, which is why I didn't write the plus, because I'm going to write the minus sign instead. So that's how you take the derivative of y with respect to x, where x and y are both given polarly. So for example, if I was given the circle r equal to 8 cosine theta, which yes, we know is a circle. Looks like this, times it, okay, got it. There's my circle center of 4 with a radius of 4. And I want to know what's the slope of the tangent line. I don't want to pick somewhere boring like here or here or here or here, because those are either 0 or undefined. Let's pick at the angle pi over 6. Yeah, I'm really asking for it over here. Okay. So find the slope of the tangent line at theta equals pi over 6. Okay, it's not as terrible as it looks. So our dy dx is going to be, so we need to do r prime. So the derivative of r is going to be negative 8 sine theta times sine theta plus r, which is 8 cosine theta times cosine theta, over r prime, which is again negative 8 sine theta times cosine theta plus minus 8 cosine theta times sine theta. And then you have to plug in pi over 6. So I'll remind everybody, sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. So when we plug this in, dy dx evaluated at theta equal to pi over 6. Whew, let's factor out an 8. Let's just cancel all those 8s, right? We can factor out an 8 on the top and the bottom to cancel out. Cool. So we're left with negative 1/2 times 1/2 plus, is that really a plus? I was really hoping it wouldn't be a plus. Sure. Plus root 3 over 2 times root 3 over 2 over negative 1/2 times root 3 over 2 minus 1/2 times root 3 over 2. Which ends up equaling, all right, it should be negative overall, right? Because definitely here the slope of the tangent line is looking like that. So let's see, we get negative 1/4 plus 3/4 over negative root 3 over 4 minus root 3 over 4. Cancel the 4s, you get 2 over negative 2 root 3 or negative 1 over root 3. That's cool. That's your slope. And if you really want to, you can find the equation of the tangent line by finding the xy coordinate here and then doing y minus y1 equals slope times x minus x1.